table of all the data. They have 3.6 times 10 to the 14 stop muon, and their sensitivity, their upper limit is 5.7 times 10 to the 13. Okay, and this is their data points, E gamma, the E, and the angular distribution. Okay, so the signal region is nothing. Okay. So they certainly will have update with the double data set, and they already have the upgrade in plan. Their upgrade, I think they are already been approved. The goal is to have a 10 times improvement to 6 times 10 to the minus 14, and they need a more intense beam. And the more important part is the better resolution. They need to have a thinner target, a larger tracker to have, and also larger calorimeter to get better coverage, and if faster calorimeter and more sensitivity to the spatial resolution. And their timing is maybe in a few years they could start by the end of the decade they would have, if all goes well, they would have this kind of sensitivity. Okay, another experiment is mu-to-E conversion. This is I got involved more in this experiment. So in this experiment we used actually mu minus instead of mu plus, because when the mu minus is slow enough in the target, it falls into the nucleus, to the atom, to the one state around nucleus, and one of the following would happen. One is that first is that it could be captured and fall into the nucleus. Okay, so like this kind of diagram, only a neutrino come out, you don't see, and you change the type, the nucleus. And this is our normalization process. And we want to see the signal, which is like that. If something happened between the muon and the nucleus, and there's a electron come out. The electron comes out, and the energy of the electron will be the muon mass minus the binding energy of the orbit. And also, it can decay. It can just decay when they are when it is in the one is orbit, and this is our main diagram. And the total rate of this decay is that, so you want to just calculate the rate is 1 over the lifetime. The normal decay is 2.2 microseconds, and the capture rate is over 1.4 microseconds. So the total decay, the lifetime that is 864 nanoseconds in the aluminum nucleus. So this is just a picture of what I just said, that it falls into one state and emit the X-ray. We could measure this for our normalization and to count how many muon falls into the nucleus. And then the nucleus radius has a few Fermi. For alumina is about around 4 Fermi or so. And the ball radius of one state in muon in aluminum will be about 20 Fermi. So there's some substantial overlap in your wave function. So how you capture that. And about decay, if muon decay in vacuum, it would go, the electron spectrum would go like this. It's called Michel spectrum, and it has a cutoff at about half muon mass. Okay. However, this happened in orbit, and it has interaction with the nucleus, the electromagnetic interaction. So the spectrum will be corrected a little bit, it's called radiative correction, and it has a very, very long tail all the way to our signal region. Okay. And this long tail falls off very quickly, but still, nonetheless, if we are talking about 10 to the minus 16, it's still substantial in this region. And the signal will be like that here. So what we want to do is amid all these backgrounds, we want to see excess at the endpoint. So this is the mu-to-E, the proposed mu-to-E experiment at the Fermilab. Well, the approval process has been pretty good. It's very well accepted. So we use the AGV proton beam, and it has a pulse beam. I will say a bit later. And basically, we have 3 solenoid sexters. One is called a production solenoid, where a proton comes in here, hit a target. It's a thin tungsten target, and a bunch of pions got created, and those pions would be reflected by this magnetic mirror because of the gradient magnetic field. It comes back this way and spiral through this transport solenoid. And in the middle of it has a collimator, and because the different charge will go different ways, the positive charge will go this way, negative charge will go that way. So we can block out one side so that you can select the right charge. And in here, a lot of pion got decays to a muon and go through here to the detector solenoid. And this is stopping target is a bunch of aluminum foil, and the muon stop here, got captured, and hopefully there will be signal coming out, or a lot of positron will come out here, and then again, it's a gradient magnetic field. The purpose of here is so that we can increase the efficiency more than 50% of the electron can be swept to this direction. And the main detector is a straw tube tracker to track the positron, and then we have the calorimeter at the end to measure the energy. The total length is about 25 meters.
Excuse me, can you simply explain what's the use of this shape? And maybe also the length. What does it really do? What does it achieve?
Mostly just you want to reduce the background, right? So everything comes here. You just sort of step away a little bit, right? So stuff coming out, junk bounce back would not directly impact your detector, right? And so there are a lot of configurations. Like for example, the one that in Japan goes like C shape, right? But this is just a lot of design choices. Everything is just a reduced background, and certainly the length is that you need certain length to let the pion decay. Right? So this cannot be too short. You don't want to be too close to production points, and also certainly you have consideration of the muon lifetime and the cost of your solenoid. You cannot have whatever the longest solenoid you want.
So what about the reducing magnetic field? How was it optimized?
Oh, here is just in the end, in the detector we want 1 Tesla, and certainly this so that determines the size of your detector, right? Because of the momentum we know. And so you want to optimize the sensitivity of the momentum, the tracker, the resolution of the momentum in your tracker. If you have a much higher momentum, if the spiral is too small, the resolution is hard. It's hard to measure the momentum. You want a larger path length in your tracker. But at the same time, you cannot have too big detector. One is way too costly, and so. 。
So
also the material, etc. You don't want to have too much material, so that's part of the oxidation process. And then, right, so the gradient is just to make the particle reflecting the particle to this.
Probably should speak louder.
Okay.
Sorry for our.
Okay, so this experiment will happen at Fermilab. This is just a picture of Fermilab. This is the Wilson Hall, or the office buildings, and there's a Tevatron, and this is the main injector. The Muon campus will be just behind the Wilson Hall, and this is a closer, more clear view. The beam will start here with the ion source. Use the LINAC to accelerate to 400 MeV, and there's a booster to increase the energy to 8 GeV. And so the bunches of muon will be sent to the recycler ring. And part of it will be accelerated to 120 GeV and send it to NOVA. And part of the beams would stay here and then get passed to this muon ring, muon delivery ring, and then deliver to the muon experiments. So stay at 8 GeV. Okay. So the structure of the beam, this is the time structure. The beam is a pulsed beam, and each microbunch is separate by about 700 nanoseconds. Each part is about 3 × 10⁷ protons. And the reason for that is that when the proton hit the target, it creates a bunch of junk, and then we got the muon arrives a little bit later, got stopped in the target, and then started to decay at 860 nanosecond lifetime. And there are a lot of backgrounds comes immediately at the time of muon arrival. Most notable is the pion. With some remaining pion will stop at the target and the decay. And pion has much shorter decay time, so they would decay away. We're waiting for all the junk and this stuff, the pion to decay away, and then we start our measurements. So hopefully there's nothing else going on here, only the muon decays. Okay. So one of the important part of the experiment is to make sure the beam, so-called beam extinction, where the number of protons between the pulses is less than, say, 10 billionth part of the proton in the pulse. Okay. And this is the stroke field tracker. It has 18 stations of tubes. It's a thin, very thin tube. We want to reduce the material as much as possible, and so each station has the 3 sectors, and the next one will rotate at 30 degrees and 30 degrees, so to cover up the outside of the cylinder, and leave the center part empty. So, like I said, most of the background is coming from the muon decay, which has a peak at about 50 MeV, and our signal has a momentum of about 105 MeV. So our signal will reach the outer part of this cylinder, but all the background most of the background would just go past into this hole without touching our detector. Okay, so this is one illustration of our pattern recognition. This is the event display of one micro bunch hitting the target, and then a particle comes into the detector. You have hundreds and hundreds of tracks, and almost all the store tubes are lit up. Right? However, so we need to find a track. The signal tracks are outside this, in all this haystack. So first of all, we look at the hits that at the outer radius, which is more likely to be a higher momentum electron, then we look at the timing structure of all the hits. If a signal, if a real electron goes through all these detectors, they will have all the hits should peak at the same time. And then so if you have the timing right, and you cut this plus minus 50 millisecond window, you reduce all the junk to this much more manageable level. And there's still a lot of there's some R&D going on to improve the efficiencies. And also then the calorimeter, the role of the calorimeter is to confirm that the reconstructed track is well measured, and it is also able to provide a seed for track reconstruction. So we can have a cluster from the calorimeter and then maybe use that to trace back to the track to the tracker, so that we may be able to improve the track efficiency. And they also can provide the trigger capability, particle identification, so that because one of the background is the cosmic ray. It can, in rare cases, it can mimic a signal electron. So we want to make sure the energy is right at the calorimeter. And the structure right now, the design is that the two disks with the hexagonal crystals. Total is maybe about around 2,000 crystals here. Each one has two APT readout. Current choice of the crystal is the barium fluoride. It has very fast, short components, less than 1 nanosecond in a UV range. We want to leverage these components. So because the reason they do this is that the track may miss in the middle. It goes to the middle. The spiral goes to the middle, and want to capture those that are missed by the first one. Okay. So this is Monte Carlo on the tracker resolution. So basically, the core part is less than 100 keV, and the most important part is actually this high side tail, because our signal will be on the higher side of the background. So you don't want to have this long tail on the high side. Lower side is less crucial. So that's why we quote this high side tail. There you can see it's not too bad. Then this is the overall sensitivity. On the right here is the previous best measurement from syndrome 2 at PSI. We're basically using the same analysis technique. And this is the very high statistic Monte Carlo. You see the vertical scale is normalized, so this is just 0.1 here, and this is a tiny beam size. So you want to integrate this area to get your number of events. And this is our signal window, and the background in this window is estimated to be less than half events. Okay? And so we expect that our upper limit will be around 6 times 10 to the minus 17. Okay? I will be taking data the early 21. Okay, so it's one slide to show you that Japan also has a very similar proposal, and they have a different design, but so again, they're looking for mu to E and the same target. They use a 2-stage approach. They would have phase 1 in a few years, I think. It's a very short beamline, and the phase 2 would have this kind of, in the end here, from target to detectors at a C shape, that they can select the momentum from here. And in the end, we reach the design sensitivity is similar. The timeline, I don't know, they say it's also similar early 2020 or so. So it will be very good competition. Okay, so we are already talking about possible upgrade mu to E, and a couple of things you need to do. One is that you need to increase the beam intensity, and you want to increase the duty factor, and you want to reduce the pulse width. And this can be achieved in so-called Project X area. I think now they changed the name. There seems to be another name called Proton Improvement Project, something. So it's hard to follow what Fermilab is trying to do. But anyway, so in that case, we can have currently the design duty factor of the current mu2E design is only 30%. The rest would be used for the NOVA or other neutrino experiments. And the Project X area, we can expect to much higher duty factor because of much better management of the beam delivery, and also we can have or consider much lower energy beam so that we don't have anti-proton background, and the shorter beam pulse that we can reduce this prompt background because the junk go through much more quickly. And we also need to improve the extinction, reduce the tracker material, and we to review that whether or not we need to very hard crystal calorimeter or faster ones. And if we are lucky that we see the conversion signal in the current mu2E, the next step is to use a different nucleus. Okay. Unfortunately, this plot is hard to see, but basically the idea is that you can calculate different new physics scenario as a function of the Z of the nucleus, and they have a different distribution. So different target would tell you, you look at the ratio, you can discriminate between new physics model. Okay. And one of the challenges is that the heavier nuclear would result in a higher capture rate, and so that shorter lifetime, so that you fewer muon which survive in the window. So that's so obviously this is still very early stage. Okay, so now move on to mu2-3E. It has been approved at PSI. You want to have a 10,000 times improvement from previous experiments. So they have the beam plus beams, and they have they use the silicon pixel detector. The cylinder here, the side view. The cylinder is here. This is a target, and 2 layers nearby, and the 2 more layers outside. And these hash areas are the timing counters, fiber and the tiles, and so they require much more intense beam from current 10 to the 8 to the about 20 times higher, and the sensitivity expected is 10 to the minus 16. The main background is mu2 nu. So they're using the phased approach. Phase 1 is called phase 1A will only have this part, and phase 1B would have additional silicons, and the phase 2 would have this complete detector started later this decade. So their sensitivity, again, the most important part is the resolution. This is the reconstructed mass. At the muon mass, the resolution is about 400 keV. And so this is the thing you expect. This is the background. After you consider detector effect, and this is a different branching fraction, the signal level of different branching fraction. So in this line is 10 to the minus 16. You probably can see if there's a signal here. 10 to the minus 17 would be small background. So now we are asking a question: how do we improve this scenario further? Okay. So it's our group. So ask this question and try to come up with some design that can improve the current PSI proposal by a factor of 10. Okay. So for the mu to E gamma, the background is that so accidental background. It's proportional to photon energy resolution squared because of the particular background distribution. And so this is one of the limiting factor for the current mu to E gamma design. Okay. So to attack this problem, one thing you can do is you reconstruct the E plus E minus pair from the mu1 conversion, sorry, the gamma conversion. So you actually measure the tracks of this pair. So it has much better energy resolution than the calorimeter. So our design is that here is the target and 2 layers of the silicon close to the target, and we put a heavy converter. Here is the lead covered 180 degrees, and and then more silicons outside. So here we say we use the thickness of the lead. We use like 10 radiation length. So basically about 10% of gamma ray would be converted. So we basically the signature would be 3 tracks. 2 of them comes out from this converter, right, away from the target. Okay, so this is the fast simulation. You get displayed. It's a bit hard to see the 2 tracks converted here and the main primary electron positon. Right. So we did some analyses. So in the current mu to E analysis, they use 5 variables: E gamma, and the angular, the opening angle, and the timing. And we have additional handle because the tracker has a very good direction power, so it can point back to the target, so that you can match this position to the positron. Okay, so we have some scenarios that tells that we can actually achieve about factor of few better than the mu1, better than MAC upgrade. But if you want to do better, you need to have a higher efficiency. So we can get a 5 times more efficiency, more layers of silicons to be able to achieve our goal. And also did some study on mu to 3E. I'll skip that. Fine. Okay. So again, this is just more information here. The future prospect of this physics can get to a few thousand TeV. And then, okay, we're going to skip that. Okay, so a few words on the tau decays. Just like mu1 tau decay is also detectable in single model. Oh, so in the B factory, you have about 1.5 billion tau pairs, and the super cat B would have many more times more, right? But still much less than the mu1s, and so but several scenario would enhance the tau decay because it's heavier in the 3rd generations. And also correlation is a powerful discriminator. You want to look at a lot of different nodes and see which model fits. So the experiment you probably know is very well the Bell and Mobar, and the event is very clean. The tau pair is very clean, so we tag 1 tau from its normal decay, like a tau to nu or tau to pi nu. And look for a signal on the other side. And on the signal side will be fully reconstructed. So the mass will be the tau mass, and the energy difference energy will be like beam mass, beam energy. So I'll show you a couple of results from Mobar. This is tau to E gamma, mass and energy. This is E gamma and mu gamma. Okay, the sensitivity is a few times 10 to the minus 8. This upper limits. It's about 482 million pairs, tau pairs. And tau to 3 leptons, or 6 combinations. Again,